Okay, so now to conclude this last lecture, I want to first go back to photons, okay? Because actually this was one of the things I promised many times. Now we back to photons, okay? How to put the dynamical photon in the formats. I mean, we already seen it in the nice lecture by David Kaplan, but let me very briefly recap. So, okay, we have seen that we have seen how to couple our chiral field to the external sources. Okay. So these are mu and mu. So I always told you these things we can use them to identify. You can use them as a auxiliary field for instance, for the photon when it's external. But now we want really to treat the photon dynamical. So we want to also look at the photon as a true dynamical field. So how to do that? Okay, and again, you've seen that the point that we know how to. So if we want to put here the photon, what we have to do is so this has flavor index, okay. We do the following. We introduce, we introduce these Q right and Q left, which we will treat as spurions. Okay. So again, why we do that? We do that because again, the transformation property we know that the Lagrangian is invariant if R goes into that. Okay. Now this is really this G act in this SU3 space. So clearly, if I just put the charge, this will break because it's just one direction in this space. Okay, the direction is a U1 group in the full SU3 space. So the trick is to treat, if you want, you can think of this as a scalar field. Okay, a scalar field that will have this transformation property. And we introduce another one. Okay. Because if the field transforms like this, then this is fine, okay? Then I preserve my symmetry. And then of course I will freeze this Q to the value that I need, exactly as we did for the quark masses. And of course, the physical value, okay, will be which is just, okay, the matrix. But this we do it at the end. First, we built all our operator in terms of the pion field, eventually also again R mu and L mu, but plus also this Q, okay? Because this will be there, and this need to be treated as other field that break the symmetry. Okay, for instance, when I look at a diagram like this, where they have the pion, okay, and here I have my visual photon, okay, the visual photon by itself, so here I have my Q, okay. If this Q would transform, this object would all be invariant, okay. Then when I freeze it, I get what I want in QED. Okay. That is the and the point that finally with this way I will get something that finally that interact pion Q. So you should really think of this as maybe. So you see this vertex, I mean that here there is the insertion of this Q field. So these things now, if I look at it like this is formally invariant. okay? Because now all the ingredients here preserve the symmetry, but then the Q is frozen. Okay. And this tells you that then I will need to build my Lagrangian with this Q in addition to the U and so on. And again, this you have seen that one does like this. There is a single unique I write it as a correction to the Lagrangian, which is, I know, what's more new notation, but okay, this is the only thing that I can build because given the transformation property of U, okay, the transform as G, did I put it correct? No, I think I put it, sorry, our U transform as G right U. Actually, in the literature, you find all the possible options, okay? Some people define U transforming like this, some other define U transforming like G left. There is a bit of a mess, like F pi divided with the square root of 2 or not. But, so I should try to be consistent, but at the end, the rule are very simple, okay? Okay. And with that, again, you have seen it. One expand U, remember, U to E square root of F. This is our, and then you get a correction to the pion mass. Okay, you get 2 pion from here, and the only terms that do not vanish are with pi plus or k plus. And okay, I don't do that again because it was done nicely in the previous lecture. So if I expand this Lagrangian, I get terms with more pions. Okay, just doing the expansion, and this gives you a correction. We call it this, which is 1 n pi plus square minus that because you have a correction only for the pi plus and not the pi zero, right? And this can be measured. So, well, now why discuss that? I want to come back to that. Then we will discuss what happens when we go to higher order. I think it's interesting to see what happens when we try to play with also with our vector mesons, okay, to see how this is correct. But before going that, let me again try to estimate what we should have expect here from this contribution. So this delta, okay, now written diagrammatically from the point of view of the Chiral Lagrangian is this contribution plus this contribution that I get plus a counter term, okay? So this is where I put this C coupling here, okay? And then this is, on the other hand, these are vertex that I get from my L2. Right? And it, as David told you last time, if you evaluate these two diagrams in dim-reg, you get 0. Because, and you have to evaluate these in the limit of 0 pion mass. Okay, we are computing this at order E square P0. So we neglect pion masses because this will be higher order. So clear here I have an integral with the photon only. Here, these are all scaleless integral. So I will always get 0. But of course, this is a scheme choice, right? One can try to do an estimate, the brute force. I would call it the brute force which, let's close a bit our eyes and look at this diagram here or that one, and let's put a hard cutoff. If I put a hard cutoff, I get the result. Okay, what I get? Well, I know the vertex here. So the vertex here comes from the Lagrangian. Okay, it's we didn't write it. Maybe we should write it here. Remember, our L2 is this is our Lagrangian. So from this term here, for instance, if I pick up the term with 2 photons, is where I pick up the photon here from the covariant derivative, right? Then I have to expand to 2 pions because I want to have the 2 external pions. So we'll get from the expansion of U, I will get a 1 over f squared that will cancel this f squared. So up to factor of 2, I simply get E squared, right? The f will cancel, then there are factor of 2, which right now I do not control. Then there is a loop, okay, which is 1 over 16 pi squared always. And then there is my UV cutoff. The naive UV cutoff, which I would expect, it's the naive choice would be put here 4 pi f, which is the natural cutoff of our EFT, right? So what I get is E squared f squared. So maybe here I put it really with wiggles. I said it because it's at the end is if you do like this and you try to match to that expression, then you see that this implies that C has to be f to the 4th, right? Because if C is f to the 4th, okay, then that is what I get there as a correction. I get a correction E squared f squared, right? Is what I expected here. And it's interesting that if you do this like this, and then you estimate, you get okay. Now I really put this number here, I get 0.9 10 to the 3 MeV squared. Now the experimental value is 1 point. I get it, yeah. So not that bad. So I wanted to show this just to say that naive counting, okay, it's already give you the right thing. So actually thinking this as the cutoff of our EFT, it's good. But we can do much better. Okay, so this is just again, and you see, then you would expect, okay, all of them are of the same size. Actually, you see, these things have to be of this size to cancel these things if you do it with a brute cutoff. Now let's do a more sophisticated thing, slightly more sophisticated. So now I go back to my theory with the vector mesons, okay? And because now we see that the vector mesons were helpful in giving the right behavior of at IQ square. Well, in that Lagrangian with that we canceled, one could have computed. Now that there are loops that you can compute. For instance, there is this diagram, and so this is the A, this is the vector. So here you will have your FA. Well, here you have your FV, okay? And here you have your GV, which is connected. Now, I told you, okay, we should not use that Lagrangian to compute vector mesons inside the loops because they are not convergent. It's true. So here I made an exception here because we know that these diagrams are quadratically divergent. They were quadratically divergent because here there was no scale, right? If I put these terms here, I will get the scale naturally. So I will get a clear indication of which is the first scale that we'll encounter in my theory, which are indeed the masses of these vector mesons. Now, if you compute this diagram, okay, it's a simple calculation. Let me just give you the result. What you get, and that and I simply use the relation between FV and GV that we know from the vector form factor. Okay, so we know that FV times GV is equal to okay. Let's come back to that later. What I get is maybe I can express this as a calculation of here. Express it like no, okay, let's do it like this. No, I do this in dim reg, okay? It was the V, the A. Yeah, I simply use the relation I express here, FV in terms of GV in terms of FV. Okay, we have this. So we know that this has to be equal to. Yeah, we know that FV GV divided by F pi square is 1, so we can express GV in term of FV. Anyway, you get this plus finite term. So the first thing is to observe what is that sorry, I told you sometimes I say stupid things. So this is also FV. This is why. So really there is no, because this is the coupling of 2 pions and the photon, which also come from FV. Okay? Because remember, FV is the coupling of the vector mesons to this F plus, which contains the vector, but plus 2 pions, 4 pions, and so on. So actually, these both vertex come with FV. So there is actually no assumption here. Just get these two results. You see clearly this diagram. Now, when I do this calculation here, you understand this, the calculation. If I do it in dimensional analysis, with dimensional regularization here, I will get well, L is the loop here. Then I will get 1 over L squared from the momenta of the, but then these two vertices are also proportional to L squared. So the structure is like that. Okay? This is why when we're doing it with a point-like interaction or with a pi interaction, I simply had another L squared would be vanishing. While here I have this. This is why now if I do it in dimensional regularization, I get something which is proportional to the mass. Right? Again, it's a very simple calculation. The key point to see is that you see here, these two diagrams are both divergent. Not surprisingly, I get a finite if which was one of our sum rule derived before. Again, it's not a surprise because the sum rule that we derived were exactly to get a good perturbative behavior, good behavior at high energy. So what with that is we ensure a good behavior at high energies of this object here, okay? Which is exactly connected to this P left right, which I showed you before. I see some perplex faces. So is it clear what I'm saying? Yeah, but the divergence, you see, the divergence here will, yeah, there will be a square, but finally the divergence is proportional to the mass of the things. You get it from dim reg, because this is quadratic divergence. So that is why the mass appear there. Okay, that is the thing. And again, do it. It's very simple. It's not that complicated. One loop, especially to compute the divergence, it's not that simple, not that calculation. And then once you impose it, okay, you get a finite result, and you can sum, and you get. Now, this is just histogramming, ignoring anything else. Well, this in the same dim reg, this would be 0, okay? In dim reg. So we are left with these things plus eventually this extra stuff. And then what we get is now there is the sum rule, so I can express everything in terms of this one. And here I get finite. Beautiful. And then if you put numbers, and also again, if you want, you can express everything just in terms of MV using the various sum rules. Doesn't matter, or you can put the experimental value, but I told you the experimental value satisfies the sum rule. Then you put experimental data on these things, and you get 1.29 to compare with 1.26. Okay, I think this is beautiful. Okay, and in this result was derived by Das in the 70s, again, before knowing anything about QCD, just with the assumption that indeed these resonances need to ensure a good behavior of this pi vector interaction. Okay? It's not, it's more than QCD. It just simply say, look, I mean, I have my ions, the coupling to the photon at the lowest order is somehow fixed by the chiral symmetry. But then this doesn't know anything about the high QCD behavior. The high QCD behavior has to be good because finally that will match into a renormalizable or perturbative theory. And what ensures that is just this exchange of these lowest line resonances in this channel where they appear. Okay, so that was the last things I want to show you about vector mesons, and now we can go back to the pure EFT. Again, I hope this gives you a little bit of a glimpse, but why these UV conditions are somehow important. And on the other hand, let me, are there questions at this point? So this is divergent dimensional regularization. Sorry, yeah. So this epsilon is for me. I did it in dimensional regularization using the Lagrangian ratio before, and this epsilon is I use d equal 4 minus 2 epsilon. So I get the 1 over epsilon, and the 1 epsilon comes from this diagram, from this loop calculation. Okay. So while you see, if here the propagator is massless. It's all massless, so I have an integral of the type. So if all massless, I have this type of integral, which in dim reg is 0. It's caseless. Now with this guy here, I put the full propagator of this guy, and then this becomes So this is the leading divergence is just this. It's just this. Right? And you see, because by the power counting here, there are momenta here that will cancel the other propagator. Sorry? Yeah, but this is proportional to MA square. Yeah, so this is now, okay, up to, this will be 1/16 pi square, MA square, 1/epsilon plus, okay, the gamma, all the other stuff, I ignore it. Okay, yeah, it's the gamma function, yeah. Yeah, I'm sloppy, so I didn't write it all the term. But that is what I put here. Yeah, sorry, maybe this, is it clear to everybody what I'm saying? Yeah. Because this is not scaleless, okay? This has a scale, which is MA square. This is what Imre picks it up. Yeah. Yeah, because of parity, yes, exactly. You remember, you have this F plus and F minus, so the one with the axial start with the one pion, then there is, while the one with the vector start with the photon. If I put the photon, which is vector, then I have to put the pion here, while here the vector I have to put 2 pion. Yeah. But that would be bad. I mean, but you see, if the chiral symmetry, our beloved G, what is it now? So if this symmetry if this were realized linearly in nature, okay, you would expect left and right resonances, or if you want vector and axial should be degenerate. Now, see what happens in the spectrum. If you see, there is the pion, and nothing else, because the pion is the Goston boson. And then when you go higher, so you have the pion, you don't have the corresponding scalar, and then you have these V and A here, which has this, the A is a bit higher, but somehow, indeed, because of the shift given by the pion, put it that way. Okay. Finally, when you put all the system together, you basically have the degrees of freedom to restore the full chiral theory in the vectorial spin one channel, because then you can combine V and pi to make something left and something right, and similarly here. No, not what I'm saying. If the quark condensate would be 0, this would be degenerate. So the quark condensate is what breaks. So the pion is massless, okay? The shift between these two is not given by the quark masses. It's given somehow by the quark condensate. Indeed, these sum rules tell you that FB, this sum rule, the first one that I was telling you that this is maybe, sorry. This was one of the sum rules, if I remember correctly, right? So you see, basically, there is, and then there is the other one that tells you that FV square and V square is equal to. So there is this mismatch introduced by F pi, okay, on the two states, which is related to F pi, what control the quark condensate, has control the breaking of the chiral symmetry, right? Okay. Okay. Okay, so shall I move? Because otherwise it becomes late. Sorry. But okay, I hope this was anyway interesting. So did we have a unit? Of course, one can also go to what happens. Well, at all the E square P square, we have introduced many more operators. It's the usual story, okay? And let's see if I. So we can compute loops. I mean, also some of the loops I showed you have also a component to E square P square. So we'll have a E square P square Lagrangian, which is of the type. Now the couplings, instead of being L, are called K, okay, historically. And so on, and then so there is an even term that you have to put if you really want to normalize the theory of this type. If you really treat your, so this is, sorry, this is Q, okay, 14. There are 14 terms. Okay, if you treat Q as I show you here, really, if you treat it as something that depends on X, you treat it as an external field that depends on X, you also have terms which contain the derivative of Q. Of course, this then you will drop in any realistic calculation, but are there formally for the normalization, they are there. Okay? And so there are 14 couplings. Basically, there are terms with two derivatives. So there are always insertion of 2Q, okay? Because so this means there are always two powers of Q left and right. So there are terms with two derivatives, which basically are 6 terms. This K1 up to K6. Then there are terms with 2I, so which means electric charge and quark masses. And these are other 5 terms. These are the interesting ones. Then we have terms with derivative, which are less interesting. It's again, there is a difference with respect to the breaking given by this Q and the breaking given by the chi. That's that we need to really introduce this derivative here because we have this Q in the loop with the photon, okay? While the chi we can really conserve it, use it as an external, completely external field. This is maybe not too illuminating, but okay, it's there. One thing it's worth to mention is this one. You see, for instance, it appears this term here, trace of Q square with this thing here. Again, here there are 2 ways to interpret this term. Actually, this indeed comes from, again, renormalization here, also of a diagram like this, but now I keep the momentum dependence of the diagram, which previously I was neglecting. Yeah, this is where, if I keep the momentum dependence, you see, this is basically is a renormalization of this term here. Okay. Now there are 2 ways to discuss it. The trace of Q square, this will be a constant. This is, I don't bother if it is left, right, because it's the same trace. Okay. This is just a number. In ordinary, in the usual sense, you can think this really is just, I can reabsorb it, giving a, now considering F as a, with that, this time really an anomalous dimension given by QED. Okay. Otherwise, I can really, if I want to keep track of the appearance of this Q, I can treat this as a separate operator. Of course, this way of keeping always track of Q give rise to many operators. And then for they don't, you can consider them separately. But the disadvantage then you increase the number of terms. Okay, of course. Usually, I mean, but in the Chiral Lagrangian, you can do that, and has this advantage of really then each term will normalize and not mix with the others. You can really have the two way to look at the problem. If this were, for instance, in a Higgs theory, this you would just treat it as the anomalous dimension of the lowest order term, right? But there is a possibility to keep track of that with this Spurion technique. Okay. Your question? Sorry? Yeah, this is the E square. Exactly. Yeah, of course, this contributes to the E square, but it also, if you look at it as an anomalous dimension, will contribute to the E square. So indeed, the anomalous dimension, just from the pure P counting, again, they really don't mix. This is the ambiguity of how you want to treat. If I want to treat the counting, so this is E square P square. Okay. So if this really I want to treat it as an dimensional coupling, this is again is P square. This is why I can consider it a mixing. Okay. And if I want to treat E as a number, I'm not really worried about it. But this Spurion technique, on the other hand, has the advantage because then you really see where it comes from. Okay? And then you know that this will be there to normalize this diagram. Okay? So it facilitates if you want the normalization. Sorry? If I fix? Yeah. Yeah, this will vanish on any on-shell matrix element, yes. But for on-shell things, this is there technically for the normalization. Okay. No, Q is Hermitian. Okay, Q is Hermitian. It's Hermitian, so I think it's okay. Okay, so yeah. Sorry? Again, so this, I think this again doesn't contribute to any physical diagram with physical pion and photon in the but you see here there is the covariant derivative, so I think you have to keep it there to normalize things which involve only external photons, I think. So it really is a sort of contact interaction that you have to put there because you have a bad behavior of diagram like this one here. Okay, so indeed you don't not only have you have things like this that you want to renormalize, so you have to put it there. Again, you will not use it in any calculation with physical pion in the initial final state. Okay. Okay. Let me move because time is fast. Finally, weak interaction. Okay. Again, with interaction, there are the easy part are the semi-electronic process, which you've already seen. So basically what one does is to replace L mu where T plus is just is just a matrix that will select the sorry here will select the corresponding transition which you see if I so this is IJ. is a bit like the case of the photon, but here I'm not interested into I treat the W as an external field. So this is basically is the charge, okay? The charge in flavor space, okay? And this is, you understand, because at the quark level, basically my Lagrangian, the way we written was Q bar left, I, L mu, I, J, Q left, there was a gamma mu, right? And then when I put this term here, okay, what I get is G over 2 square root of 2, Q bar left, I, T, plus I, J, gamma mu. So here there is Hermitian conjugate, Q left J plus Hermitian conjugate, W. And then you see this, when I plug this in here, I have Q bar Q. So what I'll get I'll get U bar left, DUD, gamma mu, D left plus DUS, U bar left, gamma mu S, which is exactly how the W couple to quark. Okay. So that this is simple. I can compute process like pion, how goes to this W that then goes to vector neutrino, or A going to Y vector neutrino. Okay. Again, it's very simple. And you just take your L2, substitute this, and you get your coupling to the W. Right. And not surprising, for instance, you can go to higher order. For instance, here, we will have this, which is exactly the same calculation we did for the pion form factor. So this is still is a vector current in this case. There will be the contribution, of course, also of this one. A pi is our beloved L9. Right, it will be fine at exactly like, so this is why you measure the pion radius. So you know L9, so this you predict unambiguously, no free parameter. One loop calculation, it's all under control. And again, similarly also here. Sorry? What transform? So what is it? No, yes, of course, yes. Sorry, of course. This I'll treat it as a spool. So my T plus has to transform as G left. Yeah. Yeah. So this, this is like, sorry, I was fast. So in principle, you can put something like, but then this is the frozen value, okay? The physical value. Exactly like the electric charge. So this is the value which then I want to get the W. Like it's a matrix which is this is non-Hermitian, and this is why I have to add the Hermitian term. Okay. Basically, it means I want to select of this L mu. I want to select only certain component because the W couple only in that way. I can do it. This is really, again, the key point is to see how in my QCD Lagrangian the W appears. It appears in this way. So I deduce, so I start from that. Then I know that the W coupling, so this is UV given. Somebody else told me that. Otherwise, I don't. So somebody told me how the W couple to the quarks. This is standard model, okay? Then I know that couple only to left-handed quarks and only with specific terms. So this is, then this I can absorb it into a special form for this L. Okay. You don't like it. Yeah, no, but yes, but here, I told you, here, this I want to treat it only as an external field. I don't want to look at loops which contain the W. The W for me doesn't know anything about QCD. So interact with the quark, that's it, and then goes away. Doesn't reinteract anymore. That's it. So this is, for me, the W is an external field where there the photon was a dynamical photon. So that is the bit. So here I did all these things to discuss these things here with the photon. I'm not doing that with the W yet. Okay. So this is why this is the easy part, which are the semi-leptonic process. So process where the W interact with the quark current and then goes leptonic. So then it's an external field. So when it's an external field, I just get it by the covariant derivative. Maybe I come back. Now let me do the other part. How much time do I have? Minus something or? Okay, very good. So then we can do. So then the other part is the difficult part. The less easy part is the non-leptonic. Okay. When, for instance, if I want to describe something like this, S to D. Okay. Here I have my S to U, sorry. S to U, and then I have my U to D. Okay, so this is, for instance, is a weak interaction. Now, coupling two quark current. Okay, this is complicated because now my W interacts with two quark currents. So now I really have to be careful because I cannot treat it just as an external field as I was doing here. See here, the point that I'm just interested in how the pion coupled to a current. So in this current, then I decide to be the W, or could it be the photon? This, all the part here deals only with QCD. Finally, when the W is emitted, doesn't go back. Why on the other hand here, the W interact with the photon. Sorry, interact with the quarks. However, still we have some tools because, for instance, we know the W interact only with left-handed quarks. Okay, so we know the transformation property of this object from the point of view of our chiral group. This is what we have to do. So these things will become a mess when we put the glue on. So this we'll have a lot of glue on correction that will change. For instance, here I have, again, S, left, U. For instance, if this were the color were alpha alpha, here the color will become alpha beta. Clearly, this changed the structure of the diagram, right? So this will be beta, and this will become alpha. Okay, but there can also be other things like this was, well, now we'll go like I can have here my SU and then the U. Okay, so if you have glue one here, I can have anything. Okay, QQ bar. So that what happens at the end. One should first understand what happens. Okay, at the level of the standard model, and what one integrate out the W in the standard model, and one write a so-called effective Lagrangian at the quark level, which is valid, however, at high energies. Okay, and this is we call it the effective Lagrangian for delta S equal 1, because I mean we are really interested only in process where there is a strange that decays into something which has no strange. But we can do other things. But for instance, in this type of process, here Lagrangian has always this structure. So it's G Fermi square root of 2, because when this shrink becomes G Fermi, then there is VUS, and then there is a VUS, and then there is a VUD. So VUD star. So it's always this structure here, and then there is a sum of Wilson coefficient and operator. These are 4-quark operator. Okay. Now these are new objects. These are 4-quark operators. So the game is simply understand how these 4-quark operators transform under my Chiral group, and then I will introduce new spurions associated to them, which now have nothing to do anymore somehow with the W, because really the only thing that, well, of course they are, there is some information from the W, but really will be contain new free parameters. So let's look at the structure of this operator. The structure of this operator, okay, we have operator, well, let me write it. For instance, there is O1, which is of the type S bar left, gamma mu, D left, alpha, alpha. So, sorry, this is U. So here, alpha, beta, and beta, alpha. These are the two things, for instance, that you get from these two diagrams. But then there are all these so-called penguin diagrams, which have the form S bar left, gamma mu, D left, times sum of the quark, U, D, S. For instance, Q3, here there is alpha, alpha, and here there is Q bar left, mu, Q left, beta, beta. But I can also exchange the color here, and I can also have right-handed, because the gluon coupled to this, but can also couple to right. Right. So how all these things transform? Well, actually, this is a simple group exercise, because the coupling of the W is an octet, because it coupled a 3 bar to a 3. Okay, and this is another octet. So basically, you have to compose 2 octets. When I compose 2 octets, this makes a lot of options. Okay, but these are not generic 2 options. For instance, the way they interact is completely symmetric. Okay, there is no special order. So for instance, the antisymmetric octet, I don't generate it. The singlet, I don't generate it. So I generate only this and only that. Okay, there's a bit of algebra to show that. Okay, you have to think of an octet is a generic 3x3 coupling in flavor space, right? To generate, for instance, this 10 bar, I need the antisymmetric combination, which I don't have here. So these are always of the form a current times another current. These current are octet, right? So for instance, this is completely symmetric. So that one can prove that you generate only these 2 structures here. So we need to find a representation in terms of our, for instance, maybe what is the octet here? For instance, all these terms here are clearly octet. You see they have a non-trivial SD structure. And this is completely singlet from the point of view of SU3, because I sum of all the quarks. So this is a singlet. And of course, all this is only about SU3 left. So my operator will transform as 8 left. So this was, sorry, S and A has to do from just is a group structure. So it can be a antisymmetric octet or symmetric octet. Here I don't tell you if it is left or right, but we know that the 2 octets are 2 left. So I need to have only an octet left and the 27 left. Sorry? the one part I would have it only, I mean, to have a singlet, I need a current that is a singlet, which is exactly the only thing where I'm not interested in, like a UU current contracted with a UU current. Well, actually, you even have it, but we are not interested in that, okay? I'm only interested in Oliver changing current. Okay. And the nice thing is that, amazingly enough, there are only at lowest order. So what I do, then I introduce, for instance, for this one, it's very simple. So I introduce a new spurion that transforms as an octet, okay? So I will introduce, let me call it the lambda spurion that transforms as G left, lambda, G left, dagger. So this is how an octet transform under SU2 left, sorry, SU3 left, right? And then I want to freeze this spurion to the value that selects exactly, for instance, this term here. So it's a spurion that selects only the 3-2 element. So my spurion will have a well-defined structure. So I will freeze it. So we'll pick up only the 3-2 entries, because I want to have a 3-2 entry. If I'm interested in this delta S equal 1, okay? And then for my Lagrangian, if I'm just interested in this part here, let me call it of G Fermi P square delta S equal 1 as the following form. There is a new parameter, which I don't know, I call it G8 because of the octet. F4 by dimensional argument, trace of this lambda. That is the only octet I can write, because you see this, if you try to take the trace, if you take lambda, so lambda, we see how it transforms, while you remember U transform as G right, U, G left dagger, so you can have U right that transforms as G left, U dagger. So if I construct lambda with lambda U dagger, transform as G left, lambda U dagger, G right, so it's clear that I need something that transforms as U here, but then if I put U dagger U, I get identity, nothing, therefore I need two derivatives. That is what I get here, right? So this is how the non-leptonic part of the Lagrangian look like. And then there is the 27 plate, which, okay, if you want, I can write it, but it's not particularly illustrative. There is also another operator, is only one operator. And this is a U dagger, the mu U. So here I put explicitly directly the spurion projected. So if we want this is equivalent to say G8 F4 d mu U dagger d mu U element 2, 3, right? Because this lambda select only the element 2, 3. That is what. While for the 27 plate, I pick up something more involved, which is of the form U11 plus 2/3. Again, this is just okay. Now, so these are two free parameters, okay? Which I don't know, because you see, basically these two things are two independent objects from the group point of view. And so how they get hadronized, I mean, it's encoded in this coupling here. which are independent. So which is the size that we expect for this coupling? So clearly they are related to this structure here, okay? And plus there is, we want a transformation of this 4-quark object into a chiral representation. So given I put here the F square, so clearly they goes like G Fermi, okay? Because here there is G Fermi. There is VUS, which is important to keep because it's a small number. VUD is about 1, so I neglect it. And then the way I put it by dimensional argument, G Fermi goes like 1 over mass square, while here this term it's no, I think it's, yeah. You see, this has 2 derivatives. So I put here an F4, which indeed is nice so that it cancels when I have 4 pions. So this has to be dimension -2, which is exactly what you expect from G Fermi. So it's exactly what you expect. Okay, so we basically pulled out the natural scale via F. Okay. Now these things now can be measured because, for instance, with these things you can predict the decay K to 2 pions, K to 3 pions. Actually, already from the K to 3 pi decays, which are basically 3 channels, right? There is A0 going to pi plus, pi minus, A0 going to pi 0, pi 0, and then there is K plus going to pi plus, pi 0. Now, in the 0 minute, let me tell you that here, you see the pi plus, pi minus, so this is 2 pions in S wave because they come from a count decays. So 2 pions, the pions bring, each one has isospin 1, right? The pion, they form a triplet, so they have isospin 1. They have to be in a symmetric state because they are in S wave. So there are only two options. The 2 pion state can be either in isospin 0 or in isospin 2. Okay, think of combining two spin 1 symmetric, either spin 0 or spin 2, right? The kaon has isospin. What is the isospin of the kaon? You see, in the old days, everybody was. What is the isospin of the kaon? It's a so it has only 1D, right? The kaons has only 1D or 1U, so it's 1/2, right? It's a doublet. So if I have a doublet, now so here we can have a transition from 1/2 to 0 or 1/2 to 2. So here we have delta I equal 1/2 or 3/2. Well, in this case, delta I is only 3/2. Okay, because I need to pass from 1/2 to 2. Sorry, pi plus pi 0, of course, has to be isospin 2 because there is this is not isospin 0, right? So it has to be isospin 2. So I'm saying this because it means that here there is both the octet and the 27 plet can contribute, while here it's only the 27. And one can prove that, okay, a bit of, this is just group theory, the delta equal 3/2 is only in the 27. Delta I refers to the change of isospin from initial state to final state. Okay. Sorry, I'm going a bit fast. So here I have my initial state, which has isospin 1/2. My final state at isospin 0 of 2. What triggers the transition are these two objects here, these two operators. The two operators, I classify them here in terms of SU3. But then there is a sub, SU3 contains SU2. And in the SU2 of the octet, there is only delta I 1/2. While indeed, you see, the SU3 of the octet contains only 1D. So it's only isospin 1/2. Okay. While the 27 plet can also do the 3/2. Okay. Then you can think of the octet just as S to D. Let's see, so it has a delta equal 1/2. So it's a very way to, so you see this Lagrangian, you expand to 3 pions, so sorry, 1 chaos and 2 pions, and you compute all the decay. And so all these are measured very well. And so you measure very well what is G8 and G27. In particular, G27, you unambiguously get it from this decay, while G8, once you determine that, you get it from these other 2 decays. And this is the interesting things that G8 is about 9, 10 to minus 6, while G27 divided by G, with this notation, okay, it's 1 over 18. So these 2 numbers, a priori, you would expect it to be similar. They all come from this term here, okay? You don't see any particular structure, while nature is, this is the famous puzzle, even before the standard model was associated, was this famous puzzle of the delta of 1/2 rule. So why the delta 1/2 transition seems to be much bigger than the delta 3? And there were tens of hundreds of papers probably on trying to explain that. I think now we have an understanding, which is a bit of a series of accidents happening. So, okay, so the natural size is this one, okay? So what is this? Maybe I should, let me put it here. So we have this G8 experimentally is 9, 10 to the minus 6, while G27 experimentally is almost 20 times smaller than G8. So this number basically, so this number, now if I put the number, it's 2.3 10 to the minus 6. So what I meant that to go to G8, basically you have to have times 4, while times 1/4, you go to G27. Now there is nothing special in the 4, okay, it's number, but so there is an enhancement here and a suppression here. The interesting thing is that this now we understand it in part from perturbable QCD. So when you look at, so this Lagrangian at the high scale, really the coefficients for the 2 are identical. Okay? Then this gluon correction, this effect here, all enhance the operator ending up in the octet. So of this factor of 4, a factor of 2, you understand it by perturbation theory. If you run down from the W scale up to, say, 2 GV or 1.5, no, let's say 2 to be conservative. If you go up to 2 GV, you see already a splitting between the 2, really a factor of 2 here and a factor of 1/2 here. Then this really explains half of the things. The other half is purely non-perturbable, but continue exactly in the same direction. Okay. And again, that is nature. So finally, this 1 over 18 is a combination of a hadronization effect plus clearly, many people argue that probably the dominant effect are these diagrams really at low energies. But again, it's hard to identify these. It's really also the anomalous dimension of this is important. So this clearly goes already in the right direction. At some point then, discussing diagrams when you go below 2 GV makes no sense, okay? You can discuss topologies, but not really single diagram because they are all non-perturbative, okay? And so, okay, and this basically conclude the story and maybe, yeah, I wanted to discuss also something about rare decays, but probably maybe we can do that in the question time if you want. But okay, so I hope the basic concepts are clear. So the key point is to build this Chiral Lagrangian, we really need to have ideas of how the object transform under this group. So here, for instance, in this case, we need to identify the absorption property and then we build the Chiral realization. Also in this case, of course, this is just what happens at order p squared. Then if you go to order p to the 4th, you need to put other term. Okay, so maybe it's a good point to stop.